maximum and minimum of a function in two variables on restricted domain or compact domain in the plane R squared. Let's begin by this introduction. I will take the function y equal fx. Let's remember how to find the maximum and minimum value of a function in one variable f. So let's take this theorem. The theorem said that if the function y equal fx is continuous on the closed interval, so the interval must be closed and the function continuous, two conditions. Then the maximum exists and also the minimum exists. So I have two conditions, continuity and closed interval and bounded interval. So this theorem is not correct if the interval closed at a to infinity. Or this theorem is not correct if the function is continuous on R. So it must be closed domain and bounded domain. So closed and bounded, this is the meaning of restricted region in R power 2. So let's take this remark. If the function y equal fx is continuous on the open interval AB, then the maximum maybe doesn't exist and also the minimum. For example, if I take the function 1 over x, this function is continuous on the interval 0, 1, but the maximum of f doesn't exist because if I take the limit of 1 over x when x approaches 0 from the right, so the answer is 1 over 0 positive, so it's plus infinity. So no maximum. The maximum doesn't exist because fx approaches infinity. And in fact, if we sketch the graph of this function, we sketch x-axis and y-axis, and if I suppose that this point here is 1, 1, this point here 1, 1. So the graph of the function from 0, when x moves from 0 to 1, this is x-axis, this is y-axis. So the graph will be something like this. So here the point approaches, the y approaches infinity, so fx approaches infinity, so no maximum. What is a bounded region in the plane R squared? Let's explain it by examples at first. Then we will see, after that, we will talk about it in general. So here I have two regions, D1, D2. D1 inside the triangle, and the parts here, the sides are included. So if I suppose this is point O, this is A, this is B, so D1, all the points from O to A are included in D1, and also from O to B, from A to B. So the region D1, we have here the line, this line x plus y equal 5. So under this line, I have x, here y equal x minus 5. This equation could be written as y equal 5 minus x. So here, y less or equal 5 minus x. And here, up of the line, y greater or equal 5 minus x. So the region D1 is given by y. I will take this formula. No, not this formula, this one. Y less or equal 5 minus x. So y less or equal 5 minus x. And I will suppose that x positive and y positive or 0. This is D1. So what is D2? D2 is up of the line. So D2, y greater or equal 5 minus x. Is D1 closed, bounded? Excuse me, is D1 bounded? Yes, D1 is bounded. because all of the points, because why D1 is bounded? D1 is bounded because all of the points inside D1 will not go to infinity. X of this point, if I suppose this point xy, so x will not go to infinity, y will not go to infinity. So D1 is bounded. So bounded means the points inside this region, x of this point will not go to infinity, or y of this point will not go to infinity. So D1 is bounded, but D2 is not bounded. Why? Because the points here in D2, x could go to infinity and y also. So in general, the region D is not bounded if for a point xy in the region D, x could go to infinity, or y could go to infinity, or both of them together could go to infinity. We can explain this in another method. In general, the region D is bounded, region D is bounded if we can sketch a circle contain this region. For example, I will sketch now a circle here contain D1. I can sketch a circle contain D1. Because of this, so now the region D1 is bounded, but so D1 is bounded. D1 is bounded. But I cannot sketch a circle contain D2. So D2 is not bounded. Now, what is the meaning of closed region in the plane R squared? The region in the plane R squared is not closed, will be not closed if there is some points around this region which is not in the region D2. For example, here I have some points here, boundary points. So here, these points, let's call it AB. The point AB is boundary, and it doesn't exist in D2. So AB is not in D2. So the set D2 is not closed. So, but here the set D1 is closed because it contains all the points around this set. So this definition is similar to the definition of the closed interval, for example, from 1 to 3. This is closed because it contains all the points around this interval 1 and 3. But the interval 1, 3, open at 3, let's write it like this. This is closed at 1, open at 3. This interval is not closed. And also 1, 3 like this interval, this is not closed. So also here, if there is only one point around the region D2, but it's not inside and exist in D2, so the region D2 is not closed. At least one point is enough. Now, the definition of the restricted region or compact region in the plane R squared is by definition a bounded and closed region in the plane R squared. So restricted region in R squared or compact region in R squared is bounded and closed. Examples. Example number 1 here. The region D1 inside the triangle and all the boundary points here around the triangle are included in D1. So I can write the triangle D1 as here. The equation of this line is x plus y equal 1 or y equal 1 minus x. So inside the triangle, y less or equal 1 minus x, and x positive or 0, and y also positive or 0. So is D1 closed? Yes, it's closed because all the points around the region D1 are included. Is it bounded? Yes, because we can sketch a circle contains D1. Is it restricted? Yes, because it's bounded and closed. The next example, the region D2 inside the rectangle here given in the picture. Let's write the equation here. Any point here, suppose it x, y. So x x moves from 2 to 5. So x from 2 to 5. I will write equal 5. Could be equal 5 because the point could be here, for example. If the point here, x equal 5, and it's possible because this side included in D2. And y of the point moves from 1 to 3. Equal 1, it could be equal 1 if the point is here, and it could be equal 3 if the point is here. If the point is here, so x equal 2, y equal 3. Okay. So is D2 closed? Yes, because all of the points, the boundary points means the points around the region D2 are included in D2. Is it bounded? Yes, it's bounded because I can sketch a circle contains D2, and any point inside D2, x will not go to infinity and y will not go to infinity. So it's restricted because it's closed and bounded. Next example, it's inside the triangle without this side. So the equation of this line is x plus y equal 1. So I will take x greater or equal 0, y greater or equal 0, and y. So remember that all of this region here, instead of this line, the equation of this line, y equal 1 minus x. So here y less or equal 1 minus x with the line. Okay, the line is included in this equation, in this inequality. So y, if I want to take y strictly less than 1 minus x, now I will take the region D3 without this line. So these points are not included. Okay. Because of this, I wrote strictly y smaller with not equal to 1 minus x. Is it closed? No, it's not closed because these points are not in the region, these boundary points. Is it bounded? Bounded, yes, it's bounded because I can sketch circle contains D3. Is it restricted? No, it's not restricted because restricted must be closed and bounded. Now, next example, the region D4. Here, between these two lines, x equal 2, x equal 3. So the region D4 is all of this part without the stop. Here, y will go to minus infinity, and from this direction, y will go to plus infinity. So because y could go to plus infinity, so it's not bounded. Is it closed? Yes, it's closed because all the points are in the boundary here, the points here. All of these points are included. So how to write this? The equations of the region D, or inequalities of the region D4. It's x between 2 and 3. Equal to, because it could be the points here. Okay. Is it restricted? No, because it's not bounded. Next example, the region D5 inside the circle of center 0, 0 and radius 2 with the points of the circle. So any point here on the circle is included in D5. So because of this, we have equal here. Okay. So because all of the points on the circle are in the region D5, so it's bounded. So any point inside this circle, xy, x will not go to infinity and y too. Is it closed? Yes, it's closed because the points of the circle are inside. It's bounded because xy will not go to infinity, so it's restricted. So theorem. Now, if the function is continuous on a restricted domain, function in two variables, so the function has maximum and minimum. So this theorem is similar to the theorem of a function in one variable, that if the function y equal fx is continuous on the closed interval AB, then the function f has maximum and minimum. So this theorem is similar, generalization. Okay, so I have two conditions. First condition, that the function must be continuous. Second condition, that the region D must be restricted. This means closed and bounded. Remember that if the function y equal fx is continuous on the interval AB, on the closed interval, and let's suppose that f has only one critical point, C1. What is the meaning of critical point at C1? The derivative at C1 is 0. And let's suppose that the function f has only one singular point at C2. So this means the derivative at C2 doesn't exist. Now let's suppose that f at the beginning, A, the beginning here, is big A, real number big A. F at the ending is the real number big B. And f at the critical point C1 is big C. F at the singular point C2 is D, then the maximum of f is the maximum number of ABCD, and the minimum of f is the minimum number of the smallest number of the real numbers ABCD. So let's take example to explain this, to understand this. This is for a function in one variable. So find maximum f and minimum f where the function fx in one variable is given by x power 3 minus 12x on the interval minus 3, 4. To solve this exercise, let's calculate f derivative x. It's 3 times the x power 2 minus 4. So let's put it 0 to find the critical points. So we will have x equal plus minus 2. So here, because this derivative always exists, so no singular points. So these 2 points are critical. Critical points. And no singular points. No singular points. Let's calculate f at 2. So the function fx could be written as x times x power 2 minus 12. So we can write 2 times 4 minus 2 times 4 minus 12, so minus 8. So minus 16. What is f minus 2? F minus 2, it's minus 2 times minus 2 power 2, 4 minus 12 minus 8, it's 16. So now we have f at 2 minus 16, f at minus 2, 16. So let's calculate. I'm using this remark here, that take the critical points, take the numbers here, f at the critical point, take f at the singular, I don't have any singular, take f at the beginning, f at the end. So let's calculate now f at the beginning, f at minus 3. What is the answer? It's minus 3 times 9, minus 3 power 2, minus 12. So also minus 3 times, it's 9. What is f of 3? So it's 3 times 9 minus 12, so minus 9. Now what is the, now let's take, what is the maximum of f? maximum of f will be the maximum of these numbers. These numbers, minus 16, 16, 9 minus 9. So the answer is 16. What is the minimum of f? It will be the minimum of this set, the same set. So it's minus 16. So we will do something similar for a function in two variables. How to find maximum and minimum value of a function in two variables. So to find maximum of a function in two variables, fxy, on a restricted domain, D, we know by theorem that this exists. Okay, so find all the critical and singular points of the function f. How to find this? Take the gradient of the function f at a point xy. If this gradient always exists for any xy in the domain, so no singular points. Then to find the critical points, find xy where this is equal to 0. After that, let's suppose that the real number a is the maximum of fx1, y1, where x1, y1 is a critical point. And let's suppose that d is maximum of fx2, y2, where x2, y2 is singular. And c maximum fx3, y3, where x3, y3 is boundary point of the region D. Then to find maximum f, take maximum the three real numbers a, b, c. Let's finish by this exercise. Let's suppose that the function fxy is equal to x power 2 plus y power 2 minus 2x minus 4y. Find maximum f and minimum f on the region D given by x between 0 and 4, y between 0 and 4 minus x. So this region is exactly inside the triangle OAB with the three sides OA, OB, AB. So because I have equal, why the sides are included? Because I have here equal to 0. So OA is included. Because I have equal to 4, because I have here y equal to 4 minus x. So the red line here is included, the line AB. So now let's find at first. So the region D is closed and bounded, so restricted. So let's write D is restricted, and F is continuous on the region D. So by theorem that F, maximum F and minimum F exist. Okay, to find maximum and minimum F, let's take the gradient of F. The gradient of F equal the partial derivative of F with respect to x. It's 2x minus 2, 2x minus 2 times I, plus the partial derivative of F with respect to y. It's 2y minus 4 times j. So if I put this equal to 0i plus 0j, I will have x1, y2. So I will have xy equal 1, 2. So this is the critical point. Is critical. So this point is critical. Okay. Now let's calculate f at 1, 2 at this point. So it will be here x1, y2. So it will be 1, 4 minus 2 minus 8. So it's 5 minus 10 minus 5. The final answer minus 5. Okay. Now let's calculate f at each side. Let's take OA, first side here, OA. any point here, y will be 0, and x any real number between x from 0 to 4. Okay, so let's take f at xy, x0 equal x power 2 minus 2x, power 2 minus 2x. This is on the interval 0, 4. So how to find the maximum of f on this interval from 0 to 4? Maximum of the function x power 2 minus 2x. Let's take the derivative of this term, derivative with respect to x of this term, x power 2 minus 2x. So it will be 2x minus 2. Put it 0 to find the critical point. So give me x equal 1. So if I put x1 here, what is f1, 0? So f1, 0. So if I give x1, y0, it's 1 minus 2, so minus 1. Okay. Then let's take f at the beginning. What is f 0, 0? Instead of x now, I will write 0, the beginning. f0, 0, it's 0. What is f4, 0? x4 now, 4 power 2 minus 8. So 16 minus 8, so it's 8. So now we have these numbers. And remember this number. So until now, the maximum of f is minus 8, the maximum 8, and the minimum is minus 5. Let's continue. Let's calculate O, B. Any point here, x0, y moves from 0 to 4. So let's calculate f0, y. So it's y power 2 minus 4y. Okay, we have a remark here before this. The critical point was 1, 2. Is 1, 2 inside the region D? Let's verify. I put x1, is 1 between 0 and 4? Yes, correct. Is the number 2 between 0 and 4 minus 1? Yes, it's correct. So the region D, the point 1, 2 inside the region D. So it's important to verify that. Now let's study this function for y power 2 minus 4y on the interval from 0 to 4. From 0 to 4. Let's calculate f when y 0. So f0, 0 is calculated before the answer is 0. When y4, f0, 4, the answer is, I will give x0, y4. So it's 4 power 2 minus 4 times 4. So it's 0. Okay. Let's continue and calculate the derivative with respect to y of this function, y power 2 minus 4y. The answer is 2y minus 4. I put it 0, then y equal 2. Now let's calculate f0, 2. So what is the answer? 2 power 2 minus, it's 4 minus 8. So the answer is minus 4. So let's put in green these numbers, this number here, and also this number here and this number. Until now, the maximum is 8, the minimum is minus 5. Let's finish by taking, we studied the function on OA, OB. Let's study the function on AB. On AB, let's repeat the function x power 2 plus y power 2 minus 2x minus 4y, fxy is x power 2 plus y power 2 minus 2x minus 4y. Okay, now on AB, any point here, the coordinates will be x and 4 minus x instead of y, 4 minus x. So let's calculate f of x 4 minus x. It will be x power 2 plus 4 minus x power 2 minus 2x minus 4, 4 minus x. Okay, let's study this function on the interval. So here, when the point here moves from A to B, so x moves, so when the point is here at B, so x is 0. And the point at A, x is 4. So x moves from 0 to 4. So let's calculate at first when x 0. So I will have f04. We calculated f04, I think, before here. We calculated f04 here, 0. And f40, 8. F40 here, 8. So it's 0. And when x equal 4, I will have f40. The answer was 8. Now let's calculate the derivative of with respect to x of fx 4 minus x. So it's derivative of x power 2, 2x plus derivative. I have, okay. We can write 4 minus x, we can write it x minus 4. So let's write 2x minus 4. Then derivative of minus 2x, it's minus 2. Derivative of plus 4x plus 4. So the final answer here, 4x, 2x plus 2x, 4x. And I have here minus 8 plus 2, so minus 6. Minus 8 plus 2, yes, minus 6. So if I put this equal to 0, so x equal 6 over 4 or 3 over 2. Okay. Now let's calculate f. So here fx 4 minus x could be written as from here, from this formula. Let's calculate, do some cancellations. So it's x power 2 plus x minus 4 power 2. Then here 4x minus 2x, 2x. 2x minus 16. So now let's give x 3 over 2. What is f 3 over 2? And 4 minus 3 over 2. Okay. Let's calculate this. So 3 over 2 power 2, 9 over 4, plus 3 over 2 minus 4. What is 4 minus 3 over 2? 4 minus 3 over 2, it's 8 minus 3 over 2. So it's 5 over 2. 5 over 2 power 2, 25 over 4. Plus 2 times 3 over 2, it's 3 minus 16. So the addition of 9 plus 25, 34. 34 over 4 minus 13. Okay, so we can write this as 34 over 4. It could be written as 17 over 2. Okay, 17 over 2, so it's 8.5 minus 13. Okay, and after that we can write it's 8 minus 13, it's minus 5 minus 5 plus a half, so it's minus 4.5. So this is my final answer. Let's put it in green here. So now after all of these calculations, let's go back and here to see what was the maximum and minimum. So minus 5 here, this is the minimum. This is the minimum of the function f. And 8 here is the maximum of the function f. The biggest number here is, so minus 4.5 I have, and I have minus 5. So the minimum of the function f is minus 5, and the maximum of the function f is 8. So here 8 maximum and minus 5 is the minimum.